Hello, my name is Kit Langton. I am a software engineer at a company called Async, and we are currently hiring in case you are interested in working there. You can Google it. Today there are going to be two parts. First is free coffee, in which I will drink some coffee because it was 7 a.m. when I woke up, which is very early for encoding hours, and explain free structures to the best of my ability. We'll get into that in just a minute. And then part two is going to be a functional effects madman against the clock live code, oh no, in which we attempt to build a functional effects library, semi-functioning functional effects library from scratch in approximately 15 minutes. So hopefully that works out. We'll see what happens. But at first, we're going to start with the free coffee stuff. So what are free structures? If you've frequented these types of conferences before, you've probably heard of free structures, particularly free monad. This gets the top billing. If you've heard of free structures, you've heard of free monad. But there are also other ones. There are free applicatives, and there are free monoids as well. If you've ever heard of the free monoid, you've probably heard that it is in fact, someone's told you that the list is the free monoid. If you are in the know, you know that the list is the free monoid. Whether or not you know what that means entirely, that we'll get into that. These things can be a little confusing. They were always slightly confused me. I sort of figured out generally how to use them, kind of. Free monad especially. There are lots of talks on that. It's very good. But the pattern, why are they all free? There's clearly they're related somehow. And you get a vague sense of how they're related, but I think I have a better understanding of that now, how they're related, and I'd like to share that with you. But before we get into the free monoid, let's talk about, we'll use that as our first example, because it's sort of the simplest. Let's talk about just the monoid, or the monoid itself, which is a type class in Scala represented by a trait. So we have this parameterized trait, and this is basically just a jumble of interlocking functionality that relates to some type A. So for a given type A, there is a empty method which will procure you, it will manifest for you some special value of A. And then combine is this binary function, in other words, a two-argument function that will combine, smush together two elements of A into a third element of A. So obviously you can maybe put the empty value in one or both of these. They're interrelated. And we're going to take a look at how they're interrelated. There are some, in addition to just these functions, there are kind of some laws you're supposed to follow. And that is the big one, the one we're going to really worry about now. There are two of them, but we're just going to worry about this one, which is that if you combine anything with empty, you get back the other thing. So combining empty with some arbitrary other value of A is going to get you back that other value of A, here referred to as X. And here's some examples of just different monoids. So there are a couple per type. It depends. So int has two. It has both addition and multiplication. And they each have their own empty value. There's this interlocking relationship between these two functions. So for addition, empty is 0, because as we know from addition, adding 0 to anything doesn't do anything to the other side. So 0 is the empty value under addition, whereas 1 is the empty value under multiplication. So that's kind of interesting. And then for list, it's the empty list. For strings, it's the empty string. For list and string concatenation, respectively. And then Booleans also have two monoids instances, one for and one for or, which has true and false as their empty instances, respectively. So that's kind of what monoid is. So hopefully that's a good recap. But now we're going to talk about what a free monoid is. So a free whatever is basically a hyperspecific, hard-coded syntax tree for said whatever. And we're going to go into that in a more detailed manner. So in the case of a monoid, a free monoid is basically a hyperspecific, hard-coded syntax tree for monoid. So once again, we have this trait here. Let's imagine we were writing a programming language where all you could do were monoid operations. That was it. Well, how would we design that syntax tree? We don't want to be fully general. We want to be super hard-coded. This is not an abstract syntax tree, but a specific syntax tree just for monoid. Well, in Scala, we would probably make a data type that had these two cases. We'd have an empty object. Let me make this slightly... Oh, that's pretty good. We have an empty object. This would represent the function call to empty, and then we'd have a case class combine, which would represent our combine function call. And it would take two sort of inductive values of, I called it phronoid here to save on horizontal space that is not in the literature. This would be a free monoid. This would take two inductive calls. So this might be another empty in here, or another combine, sorry. And then at the leaf nodes of this sort of, it's kind of like a valueless tree. It's a syntax tree. However, this is obviously useless. We can sort of simulate the patterns of composition for a monoid by like nesting deeply, but at the end it's always just going to be empty. So we would like another property, and that's what this little asterisk represents. So it's this a free whatever is this specific hard-coded syntax tree for the operations, but also you need the ability for a +1. You need a passenger on board. So we'll see what that means. We've just prepared our syntax tree with a type annotation here, just adding a little variant A there to combine. So everything gets an A. And then we have to add this carrier. We have to let an arbitrary value ride along on this monoid experience, the monoid experience. So any value can come along and pretend to be a monoid for a day and live as a monoid lives. It's going to be very exciting for that value. It can be combined and emptied. It's kind of like you're entering a roller coaster, maybe one of those like Superman roller coasters. You are not Superman, yet you can enter the Superman roller coaster. The Superman roller coaster will simulate all the Superman-like things flying through dinky reconstructed cities, and then you will get off and throw up, and you are no longer Superman. But nonetheless, for the day, you get to pretend for the moment. I don't like roller coasters, but maybe it's a valuable metaphor. So that's that. But what about the list? This is not a list. This is not quite a list. But if we take a closer inspection, we'll see that we kind of have a redundancy here. We can either combine on the right or we can combine on the left. This can sort of be totally left-leaning or totally right-leaning. We actually don't need that. That's too powerful. We can just get away with one inductive call, and then given two free monoids, we can just smush one side, place one inside of the other's inductive slot, if you will. And then that would free us up to delete the other side and sort of allow that other side to serve as the passenger door, so we can be a little more efficient. And if we were to do that, and also do some renaming, we might end up with something like this. So free monoid or phronoid is renamed to list, empty is renamed to nil, and combine is renamed to cons. And then we've deleted the inductive call at the tail and replaced it, with the word tail, and we've deleted the inductive call, at the head, this x, and replaced it with just sort of the value property. So this has all the same power as this, but it's no longer a direct translation of the abstract syntax tree, which is, I think, one of the reasons when you look at these free structures in practice, they're often slightly reformatted, refactored to be made more efficient or easy to work with. Maybe there's a redundancy. You don't need all of these cases to be listed out in practice. But I have found that made it harder for me to understand what was happening. By a free structure, it really is just this syntactic data version of the trait, of the type class, with the ability to have a value ride along on it. And then, why is this useful? Well, it's probably most useful in the free monad case. At least there are the most talks about that, and I recommend taking a look at. There are tons of great ones. Hopefully this sort of gives you an intuition for what that structure is and why it looks the way it does. Why it's useful is, for any reason that a syntax tree is useful, it lets you sort of defer the interpretation. It lets you delay, make optimizations. You just have this data structure. When you use the monoid type class directly, every time you combine, you lose all the history. You get back another A. You've smushed away the past, and all you get back is another A. Whereas here, you don't actually get that final value, but you have sort of a recipe for constructing that final monoid, and then you can run it or interpret it sometime, or pretty print it, or do whatever, optimize it, etc. And one just last interesting thing to think about with this is that in terms of interpreting, there's a list function that you're probably aware of called fold. There's fold left and fold right, but also in Scala there's just one fold that just has the type parameter A for each operation. And if you squint at this and compare it up to this, you can kind of think of fold as being an ad hoc version of the monoid type class, where empty is this z value, and combine becomes this operation, especially when you make everything the same type. So that's kind of fascinating. There's this weird duality between sort of type classes, traits, methods, and data structures, and you can kind of twist back and forth. I think that rabbit hole goes very deep. I am slightly, I'm not a master of this stuff, but there's something there, man. It makes you think. It gets my brain all tingly, and I wanted to try to share this before I get too cursed by knowledge and too high up in the tower to even communicate with anyone. So hopefully this is helpful for someone who has been confused by free structures. And in just 2 seconds, we're going to take a look at the same thing for monad. So ignoring what monad does, we can look at this trait, which is pure and flat map. They're these ugly, complicated functions. And let's just take this 2 steps. to make a free monad without even having to understand what it is or why to use it, just by following those set of rules. Make a super specific syntax tree called a phonad here, which has these two cases. It's another sealed trait. Pure is a direct mapping of pure. Flat map is a direct mapping of flat map. The value that's being wrapped in this case is this higher kinded value, like a list or an option, something that takes a type parameter. So whenever we refer to that is when we're going to do the recursive inductive call to our syntax tree. But otherwise than that, it's kind of a direct translation, which is certainly ugly because of all the type annotations, but it's the same idea. And then we need also this sidecar, this ability to lift any value into that sealed trait to ride along and pretend to be a monad for a day. Any functor can be a monad. That's kind of the idea. You build this sort of roller coaster for monad, and then you let people onto it. That's probably a little confusing, but the Monoid version is a lot simpler to look at, I find. Just a pretty direct translation of the syntax tree. But that's the introduction. That's part one. Now we're going to get into live coding time, and we're going to hopefully see how that's related. Keep that idea of free things in the back of your mind as we sort of go insanely, madly through developing a functional effects library from scratch. So now we're in IntelliJ, and we're going to see what happens. This is going to be exciting. I might run out of time here, but I've got my stopwatch handy, so we're going to see. This is going to be fun. So we're making something, an example IO effect. I'm going to call it XIO, or we could just call it ZO or something. And I have a series of these little test cases, the whole TDD aspect of this, in which we're going to try to make these pass one at a time. And it's kind of the goals for each little object, each little trial is going to be arbitrary. I will explain them, and then we're just going to kind of just implement them as dumbly as humanly possible, for the most part. It turns out we can't be as stupid as I was hoping to be, but we can be a little dumb, a little naive, a little obvious. So the first thing we want to do is be able to put any value inside of a effect, inside of a ZO. So we're going to make this succeed method. And what goes in must come back out. So we expect that when we run this example, we're going to get the number 12 back. So I made a little helper function to print out the results for us. ZOs, the function we're going to need to make on every sort of instance of ZO is going to be this run function. It's going to take a callback. We're going to give it a function that will accept the final value, because this will eventually represent asynchronous code. We can't just get back the A. So this will sort of subsume both synchronous as well as asynchronous values and let us run both. So we're going to do that. Let us get right to it. This is going to be sort of madman pace, so let's see what happens. I'm going to create a method called succeed, and this is going to, as I said, take any A value. So not an int. Thanks IntelliJ, it was trying to be hard-coded for us, and that's very nice of it, but we want to take any value. And then the question is, what do we do? Well, thinking back to our little free lecture right there, we're going to just be very silly and make an AST representing the idea of succeeding. We're not going to actually do anything just yet, but we're going to make a case class called succeed that takes an A, and this will extend a ZO of A. So, we made the type work just like that, just by kind of faking it, making a thing. Of course, now we need to have this function here, this run function. So how do we do that? Well, run gets a callback, and we need to feed it an A. Well, what if we just feed it the A that we're storing? That's pretty easy. And now I can try running this example, and we'll see what happens. Compile. And it worked. 12 went in, 12 came out. Beautiful. Next step, zipping. Say we had two values, an int and a string. We might want to zip them together such that we get an effect of them being combined into a tuple, them being all tupled up. So we want to smush the ZOs together. So we need to define a zip method. Let's create a method called zip, which is going to take a B, a ZO of B, which I will call that, and we're going to get back at the end of the day a ZO of a tuple of A and B. And so how are we going to do this? This sounds a lot harder. No, it's not going to be hard at all. We're going to do the same thing again, making a case class called zip, and then putting this and that inside of there. And we'll worry about how to interpret this at a later date. So let's make a case class called zip. We need to add the type parameters for A and B. And there's this and that. That's probably not a good name. I'll say LHS and RHS. And this will extend a ZO of a tuple of A and B. And then, of course, we need to once again implement the run method. And in order to do this, well, we need an A and a B. How are we going to get that? Well, we have an A inside of the left-hand side. So we can run the left-hand side, and this will give us a callback with the A inside of it. So now we have access to the A in this function, and then we can do the same thing with the right-hand side, running that to get the B. And then at the end of the day, we can call our callback with the tupled up A and B. So that's a little more complicated than succeed, but it still works. And we can now try to run our zip case and see if that succeeded, or if I've done something horribly wrong in my celerity. It worked. Beautiful. 12 and hello, they're tupled up. So next up is map. We might want to be able to map values. It's a great thing to do. Now that they're in this box, we can't really interact with them anymore. So let's allow us to transform the values in the zeros. So I'm going to have a map function. In this case, I want to multiply the number 12 by 12. So I'm going to make a function called map, and it's going to take an f from a to b, a being the value that's already in the zeo, and then b being the result of this function. And this is going to get us back a zeo of b. And how are we going to do this? Well, it shouldn't be a mystery anymore. We're going to make a case class called map, passing in this and passing in the function. So giving it all the ingredients it needs, basically as though it's an AST for this operation. We're going to create the case class map. We're going to add the type parameters a and b. We're going to store this zeo in there, and we're going to have this function from a to b, and this is going to extend a zeo of b. Wow, a lot of talking, a lot of typing. I'm sorry, I warned you this was going to be slightly frenetic. And then we need to do this callback thing. It takes a b. We don't have one yet. The only way to get a b is to give it an a. The way to get an a is to run the first zeo. So we'll get an a in here. Then we can call f on that a, which will get us back a b. And then we can call our callback with that b value. It works. It's done. We can run this. It will succeed. Amazing. Next level of complication, we would like to wrap not just values, but effects. So here we want to wrap the print line effect and have this not run right away, but run whenever we actually run the zeo containing it. So let's take a look what this means. So we're going to take an a, but instead of just before like a plain a, this is going to be a call by name parameter. So this is going to lazily evaluate and sort of trap the computation in there until we access it. So we're going to make another constructor. I'm going to call it effect. And instead of just putting the a in here, because that will actually run the call by name parameter, we can suspend it by just making a thunk. So that should work. Let's make a case class called effect. This is going to be parameterized on an a. This will extend a zeo of a. This is going to look exactly almost like succeed, except instead of just being able to pass along the a, we have to call the a because it's now a function. But other than that, it works. So this allows us to suspend effects, which is kind of cool. So I can run this, and we should see that it will have print the word whatever. And if I don't have the assert function, which runs the effect, it will print nothing at all, which is what we want. And if we run it multiple times, it'll print it multiple times. So we have to move on to flat map. So flat map is very useful because we might have a zeo of some value, and we want to call a function on it which returns another zeo. If we just did map here, what we would get back is, at the end of the day, a zeo, sort of an unresolved zeo, a nested zeo. So we're going to get back the effect itself. Nothing's going to happen. It's not actually going to print this. So that's where flat map comes in. It's going to both map, but then also run the thing on the other side. So this is going to look almost like map exactly, except this takes a f that goes from not a to b, but a to zeo of b, but still returns us a zeo of b. So this looks almost identical. We can make a flat map. This f, very similar, even though the implementation is going to be slightly more complicated. But nonetheless, another AST that takes the exact same values. It's going to return a zeo of p, and then we're going to implement the run method. So how do we do this? Well, we need a b at the end of the day. So we have a value, and we have a function that takes an a. So we're going to get the a out of this initial value. We can call a on this. We get back a zeo of a, which we can call run on. But this time it takes a callback that takes a b, which is exactly what we already have in scope. So we can just pass that along there. And that should work just fine. So let's see if this indeed does print out Edgar Wyby Dijkstra, the man who hates spell checkers. Edgar Wyby Dijkstra did print out. So that's beautiful. Amazing. And now we have we're ready to go. Okay, we got this. I think I might be going too quickly, actually, I realized. I think I have more time than I thought. I don't just have 20 minutes. I have 30 minutes. That's okay. This is good. This is good. Oh, okay. I can kind of relax a minute. That's great. Now we're going to do something a little more complicated. We're going to introduce the ability. This is getting complicated, though, so we could use this minutes ahead of us. We're going to add something called async. So this does need some explanation. Async, it's kind of like an interface that allows you to interact with maybe a callback type API. So if you're familiar with how promises work, the way that this is going to work, we're going to pass in a function. This is a function definition that we're passing into async that itself takes a function called succeed here. When we call succeed with a value, it will trigger this zeo to succeed with that value. So in this case, we are starting up a future, actually, printing start, waiting a second, then succeeding our zeo, and then printing done. So when this thing finally runs, we should see start, we should see the output of our little assertion here because we've succeeded, and that would have completed that. And then at the end, afterwards, we'll see done. So it allows us to do things asynchronously, and this is going to power the next really cool feature in just a minute. But this is going to be a little complicated just because of the way this looks. But let's think about the type that we're passing in here. It's going to be, we're passing in a function that takes a function that accepts the a value. So what does this mean? So we have an a value, and we're going to have this register function, which is going to be a function that will eventually return unit, or rather any. It doesn't really matter what we get returned from that. And then this is going to be a function that takes an a and returns a unit. So that's our success callback. We're going to call that function in the other function when we want this to resolve. And at the end of the day, this is going to return a ZO of A. So that's complicated type signature, but it's not going to be complicated to implement because all we do is call async again and pass in a register as usual. So it's just it makes things a little clearer, makes things easier. You don't have to think. You just make the syntax tree. Think later, which is good when it's early in the morning and you haven't had enough coffee. So let's make this extend a ZO of A and then worry about how to implement the run method. This actually isn't going to be that bad, because what is register? Register is a function that we have to call, and what does it accept as its value? An A to unit. Where can we get one of those? Oh yes, it's the callback. Because the callback is basically the succeed function. It's the function that, in this case, just completes our ZO effect. So that's all we need for the implementation. It's actually pretty easy, I think. Let's see if it succeeds. For reals. Start, expected, success, done. So that's the exact order. It took a second in there because we waited a second. So that works. It's succeeded. And now we can do the really complicated thing with that piece of infrastructure in place. So this will be the crowning achievement. We have enough time to do this. This will be exciting. We're going to do concurrency. Okay, concurrency. We have some expensive computation. Just doing a big list sum. It's going to print out when it's starting and when it's done, and then it's going to return the result. We want to be able to do this computation twice in parallel. So we want this function called fork, which will return to us something. We need to return something that we can then grab the result eventually of that running computation. It's kind of like a future, honestly. It's called a fiber generally, but if you're familiar with futures, it's kind of like that. It's handle on an ongoing computation, such that we can then call join. There will have to be a join method on fibers, which will then finally block on the result and wait for it there. But by forking early, we can let these two fibers work in the background and then join them when they're ready. So while we're waiting on the fiber to finish, well, fiber 2 is still running too. So they're going to work in parallel. Super complicated. It's going to take a few steps. We need this thing called a fiber. Let's start just by getting in there, doing type level programming, ignoring the fact that we have no implementation. So let's make a method called fork. What do we want from this? Well, we're calling it within a for comprehension. So that means we need a ZO. We need to get a ZO back. And this is going to be a ZO of a fiber of A, which doesn't exist yet. So let's make that. Ooh, I have some variables up there. Okay, so we're going to make a class actually called fiber, and it's going to be a fiber of A, and this is going to actually take a ZOA. So this is just going to sort of wrap a ZO, and we need two things. Well, we need that join function, and this is going to be a ZO of A, though it's not just going to return the ZO that we have. We're going to see what that does in a second, and we also need to start this. We need to kick this off in parallel. So start is going to be a function that returns unit, and what we can do here is, well, if you take the hint up here that I pre-imported, we're going to submit something to a global execution queue. Maybe not how you want to do that in practice, but this will work for example purposes. You can make a custom bespoke queue on your own time that has the right number of pooling and threading and all that. But global will be a fine default for now. So what do we want to do in here? Well, we want to run the ZO. And then at the end of the day, we're going to get back some value. And the result of this value is what we want to return to join. But obviously these are two separate functions, so that's why this class is a class, and it's kind of this mutable thing, because we need a way of facilitating. We can't just sort of throw this method, even though the arrow's right there, into this return result. That doesn't quite work. So what we're going to instead do is make a var called result, which is going to be an option of A, and we're going to start this off as none. And then when we finally finish, we're going to override result to be a sum of A. And so then in here, we can say a ZO, this is the whole point of async, by the way. So we have this success function, and we can call that with our value. So in here, we can check on the result. If it exists, we can just call success. It's already succeeded by the time we've called join, in case this is like an immediately, if it was a very short, easy computation, it would have already succeeded. But the tricky part is what happens if it hasn't yet succeeded? What do? We need to wait something. So it hasn't yet ever been called. That means this hasn't been called. That means we can put something in place. So this prepared this by storing a value off, and now this can prepare start by storing some value. Obviously it can't store the result, but it can store the callback. So I can make a val called callbacks, and this can be an array buffer of functions from A to unit. And this can start off as array buffer dot empty. And then in here, all we can simply do is take this callback and say, okay, we're not ready for you yet, callback. Please await. And then in run, when we've finally gotten our value back, we can go through all of our callbacks, call for each on them, get the callback, and call the callback with the value. So we've handled both versions where it might be done and might not be done. Wow, that's intense. That's a fiber. The other side, though, is going to be in actually implementing fork. What are we going to do? The same thing as always, friends. We're going to make an AST that simply stores this inside of fork. And it's going to have to, obviously, return a fiber. So this is going to store some ZO of A, and this should extend a ZO of fiber of A. So how do we implement this? It's going to be straightforward. We've already done all the hard work. We need to make a fiber, first of all. So that should be easy. Fiber is a new fiber of A, and it takes a ZO. We have one of those. Then we can call the start function, which will kick it off on a separate thread. And then we can call our callback, passing in the fiber. Okay, that's intense, but it's done. And let's take a look if this works. I hope I didn't screw anything up. Okay, it worked. That's awesome. Let me explain what's happening. So we call two expensive computations. We fork each of them, so they each print start in parallel. Then we get to this line, which prints 3 dots. Then they each finish, print done. And then the entire overarching ZO finishes and returns the sum of those two computations in parallel, which is awesome. And now we have so much power under our belts. We can already use fork comprehensions, obviously, because we've implemented map and flat map. So that's cool. We get that for free. Also, now we can make these higher level combinators, just like zip par. So we have these two functions that just iterate or print out the numbers 1 through 7 and then also the letters A to G. And we can implement this super trivially. In fact, it's going to look almost exactly like zip. In fact, I will just, instead of implementing that like this, I will steal zip. I will rename it to zip par. And actually, another thing, just as with the free monoid, we were able to refactor and delete some complexity. We no longer need zip anymore, or map, because these are both less complicated than flat map. Flat map kind of subsumes both of them. So we can delete all those members of our syntax tree and re-implement them in a more sort of foundational API. So by changing map to flat map, our function of A to B no longer works, but we can chain onto the end of that because we need to return a ZO of B for flat map, and we can just call ZO.succeed. So we can take that B that we get out of here, not ZO, ZO. What's ZO? ZO. And that will work there. For this, we have fork comprehensions, and this is going to make it a lot easier. So we can get our A out by binding on this, we can get the B out by binding on that, and then we can just return a tuple of A and B. That's really nice and easy to read. And then we can make zip par, our final sort of goal here. But instead of just returning these, we want to fork both of them. So we fork both, which will get us back a fiber for each. And then we can get back the actual values by calling fa.join and then also fb.join. So we're doing the same thing, except it's in parallel using that sort of underlying fork combinator that we came up with before. I can run this. We should see both letters and numbers intertwined as they print to the screen because they are running in parallel. I might have to run it a few times depending. But no, 1, 2, 3, 4. Okay, so they ran sequentially there. Which is sad, but sometimes they should run differently. Maybe at this end I'll be unlucky. There we go. Nope. Yes. 1, 2, 3, 4, 5, A, 6B. So because these are so small numbers, it depends on how they're whatever. If I made this like 1 to 1,000, we'd see more interleaving. But nonetheless, it is running in parallel. We proved that before with this. These values are kind of small, so it hasn't quite worked. But that is that. I have approximately 30 seconds or so left. So I'll just take a deep breath. I hope that was interesting. Certainly we couldn't be as stupid just due to time constraints as I would have hoped, but I hope you see sort of the correlation between free structures and this. Really, functional effect systems are kind of a free monad with a bunch of other features piled on top of them. But really, at the end of the day, there is syntax tree, an abstract syntax tree, which lets you do all sorts of crazy business and optimize them. And because it's a description of a computation instead of an ongoing computation, you can do all sorts of cool combinators. But don't have enough time to get into everything. I hope that was educational, and hopefully I've recorded this, and you can watch it in slow motion in the future. Okay, live coding time done. I'm going to stop sharing my screen so we don't get a giant recursive thing. Thank you.